Okay, so first of our extra tutorials, I'm going to load up the Space Invaders game at the point where I left it last time, and we're going to try and add in a particle system. But along the way, we'll also learn a few other new things that are worth learning, like how to go through a for loop backwards, which is quite often useful. Aggregation, a little bit of that. What else? We'll find out as we go along anyway. So here's where it was at the end of the last video. Shoot, destroy alien, don't fire back. You don't fire back yet, but that was for you to complete. And I think I'll turn down the volume because that was kind of loud on the music there. So when you play the background music, oh, sorry, wrong bit. You can then change the media player's volume. I'm going to set it to maybe a quarter. That should be a bit more reasonable. You can also do the same for sound effects at the same time you play them. So hopefully you can hear me over that. You know what? Let's make it even quieter. Oh, wait a second. That'll be why. That's better. Okay, right, so we're going to make the particle system, and to make it more useful to you, I'm going to put it in a separate class. So let's add, right click on the project and add a new class, and let's call it particle system. So although it's going to create a class called particle system for us, we actually need two different classes, so I'm going to change that a little bit. First is the class for the actual particle itself. Now, particles are a very broad ranging topic and you can do tons of things with them, but they all have a couple of things, or rather nearly all of them have a couple of things in common. Like they will all have, let's make a few variables in here, they'll all have a position. There's not much point having a particle if you can't render it somewhere in the game. Right, and because this is a brand new class, we'll need to put in a using for the vector, so we have access to the vector structure. So the particle has a position. We'll need what's called a TTL, time to live, and that gives it a certain amount of time, and when that time runs out, the particle will get deleted. It dies off. I'm also going to give it a texture. Let's resolve that as well. That's all you really need, but there's not much you can do if all it is things spawning and moving for a certain amount of time. So I'm going to add a few more items, which you should kind of consider optional, but we'll give it a velocity so that you can control its movement, a scale so that things can get bigger or smaller, a rotation, or maybe orientation is better word for that. No, stick with rotation. But also a rotation speed so that it can change rotation as it goes along. And one last thing, we'll put in a colour. And of course the colours that you apply when drawing aren't really colours as such that you see, they're tints that are applied to the existing colours, so I've called it tint. That's all the data we need. All we really need to be able to do with it as well is draw, because particles don't tend to interact with other elements in the game. Sometimes they do, but the basics of our particle system is just aesthetic. So to draw the particles, we will need to know the name of the sprite batch to draw with, so I'm going to call it SB. And we're going to use the sprite batch to draw our texture. And where we draw it, it says rectangle, but I'm actually going to use position, which is a vector, like in version 2 of the draw command, texture, position, color. But I'm not going to put the color in. Instead, I'm going to go to what versions I'm actually using. You know, I'll fill in the parameters first. I'm going to put a source rectangle as null. So a source rectangle is used to draw part of an image, like if you've got a sprite sheet and you only want to draw one frame. That's not what we're doing, so we're going to leave that as null. Then comes the tint. You can add in things like rotation for these other versions of the draw command. The origin, I could actually define an origin as a variable, but this is the only place we'll need it, so I'll just create a vector on the fly right now. I'm going to get texture width divided by 2 as the x coordinate, and texture height divided by 2 as the y coordinate. So that will give us halfway across and down the texture is its origin that it will rotate or scale around. The line's getting a bit long there. So I'll put the comma in. Next thing we got is the scale, and the what version are you using now? This one. So there's a scale. We need sprite effects, and that is an enum. So we need to do sprite effects dot something. I'm going to say none. We're not flipping it around or anything like that. And the layer depth is sometimes useful, but we're not going to make use of it right now. So we'll put that in 0. And there's our draw command. I'll split it up to make it a bit more readable. Okay, so now we've got a particle and it can draw, but that's not really a particle system, that's just a particle. We then need something that's going to emit the particles. So that of course is their particle emitter. Right, so we need some kind of RNG. I'm going to make it private and static. Private because nobody else needs to use our RNG, but also static, so that means there's only one of them for all particle emitters. So we don't share, we don't have individual copies of the RNG. If you spawn 2 particle emitters at the same time, then they will be seeded with the same timestamp, which means they'll have the same random sequence. And we don't want that, so static will avoid that. Okay, so what do we actually need to get this thing kicked off? Well, primarily what we need is a list of particles. I call that list particles, of course, it makes sense. And we're going to initialize it as the constructor. So we construct an empty list of particles. Each particle then has its own position, texture, velocity, etc. And the particle emitter will decide when to create them and when to get rid of them and stuff like that. So what should the TTL be for each particle? We could set it manually every time, but I'm going to give it a default value. I'll make it 500 milliseconds. And it's public, so we can overwrite it. I'm not going to turn it into a property. That would be a good thing to do, but I'm going to just keep things quick here. Let's go for the default tint as well. I'll assume things are white unless we're told otherwise. And a texture, kind of a default texture as well, I guess. Okay, and then we get onto the various properties that the emitter can use to get the particles moving around and doing stuff. For example, we have a minimum source vector, so that will be the top left corner of the spawn area for particles. The source where the particles will spawn. And then the max will be the bottom right area. So between those two vectors, you've pretty much got a rectangle. Could have used a rectangle, but we're going to generate vectors, so I think it may be easier to interpolate between those two. So that's the kind of area we're going to spawn particles in. Next, I'm going to do a minimum velocity. Let's give it a default value as well, so that we don't necessarily need to set this up every time we create a particle system. And as you might have guessed, we can have a maximum as well. So if it's got a minimum of -1, -1, and a maximum of 1, 1, then it's going to spawn somewhere in a cube. Sorry, not spawn somewhere, but spawn with a speed that could be anywhere left, right, up, or down. But it's not a circular kind of motion; it's spread within a cube shape. So just bear that in mind. Scale as well. I'm going to make that a vector too, rather than just a float, because then we can scale things up more horizontally than vertically. Oops, sorry. spelled it wrong. So new vector 2, somewhere between 1 and 1. I'm really just initializing this to make sure that it does have a scale of 1 unless you choose otherwise. Because if we left it at 0, then obviously it would be scaled down to 0, your particle wouldn't exist. Next, the rotation. That is a floating point rather than a vector because it just represents an angle. And it's in radians, so the lowest is a negative float, which is pi over 2. Whereas the maximum would be a positive float, pi over 2. So it's going to have that amount of rotation either to the left or right. Oops, hello. You can see a sort of pattern emerging here. There's nothing too strenuous going on, but there's a lot of things, a lot of data needing to be dealt with. Minimum rotation speed. This is in radians per update. Oh, my keyboard being funny. Minimum alpha, so that's a transparency. You could interpolate over time for all of the different components of the colour, but I'm really only going to do the alpha because that's the most common one, is to have particles fade out. They'll have an acceleration. They'll have a growth, so they can change scale. In fact, you know what, I'll do growth. I'll give you two options for growth. You can grow linearly. I'll assume you don't actually do that though, so we'll set it to 0. That's public, so you can overwrite that. And exponential as well. So that means it grows quicker or slower over time. Or shrinks, I suppose it could be. I guess we'll need something to kind of slow it down over time. So we'll slow down its rotation and its velocity. There's no reason you couldn't make this accelerate, I suppose, with a negative number. Depends on what you're doing with your particles, because particles can represent all kinds of stuff: smoke, fire, lightning. I've seen people represent flying animals and vehicles in the distance as particles. So there's tons of stuff you can do with this. As I said, alpha can change over time, so let's represent how much it changes by. It's going to fade out gradually. Now, you can either spawn particles all at once, or you can spawn them over time. So if you're doing it over time, I'm going to give you a variable that controls how many you spawn every second. I'm going to work out, based on that, the time in between particles. So if there's 1 per second, then there's 1,000 milliseconds in between. If you change that, then I'll need our program to respond by changing that as well. In fact, we don't really need access to that. Let's make it private. Sorry, we don't need access to that from elsewhere. Now we'll also need a particle spawn timer, if we're doing that, which is going to count up to that number. So this timer starts at 0, counts up until it gets to 1,000. That's when it spawns the particle, and then resets back to 0. Of course, you could ignore all that if you're just going to have an explosion which just spawns 1,000 particles all at once. That's fine too. I guess that's probably what we're actually going to do. Okay, so how do you actually use this? Well, we need to put in a few methods. I'm going to, first of all, a really simple one to clear out the particle system. I don't want that, those empty particles lying around at the end of a level, for instance. some kind of method to spawn or emit particles. How many do we spawn? You tell us. How do we do that? Well, we'll make a loop. The index starts at 0 and it keeps on going as long as it's less than the number you specified. So that will do, let's say you say emit particles brackets 10. The number becomes 10, it goes I from 0 to 10, and it runs this code 10 times. So what's it doing? Well, it's creating new particles. So we create a particle, I'm going to call it P, that's a new particle, and then we add that to the particles list. Simple so far, but in between we need to set up a whole bunch of stuff, like how long does this particle survive for. So we use the default time to live and give that time to live to that particle we just spawned. Give it a texture as well. Give our texture to the particle's texture. Give the default tint to it. Oops, default tint. But the alpha might be random, so oops, what am I doing? The alpha might be random, so we're going to take our math helper library and use lerp. Lerp is linear interpolation. So linear interpolation worked by giving it two values, one being the minimum, one being the maximum, and the other being how far along the line between those two we want to be, and over time that value can change. But right now we're not changing it over time, we're just going to get a double. We used random next before, but now we're going to use random next double. As you can see, it gives us a number between 0 and 1, but it's a double precision, so we need to convert it to a floating point. Okay, so that's basically a random alpha. Except that's obviously type multiplied by 0 to 1, so I guess we need to scale that up by a factor of 255 because the alpha should be somewhere between 0 and 255. And finally, that alpha is a byte value, so we need to cast it to a byte. Okay, so basically that's going to give us a random amount of scale between the minimum and maximum. And that's a pretty common theme we're going to be seeing a lot here. We've got a minimum and maximum that spawns with. We need to randomly choose a point between those two, and that's what lerp is doing. Choose a random point and lerp between those two according to how far along we should be between one and the other. What have I forgotten? I've got a bracket there, have I? Yeah. Okay, so that's our tint figured out. There's a whole bunch more like that coming, so I hope you followed that. For example, where should it spawn? Well, it's going to be a vector 2. I'm going to have to work out the x and y values, so let's do the x first. Again, lerp between the minimum x coordinate and the maximum x coordinate, and we're lerping by a random amount. Fat fingers. So we lerp by a random amount, and that gives us a random proportion of x and y. Okay, and I guess we do something similar for the y coordinate. Obviously it's minimum y and maximum y. Okay, put the comma there. So that's our position. It's randomly spawning somewhere in the box defined by the minimum and maximum x and y. Next up, velocity. Similar kind of idea. In fact, I'm going to copy and paste and see if I can make this fit a lot easier. Yeah, we've got the minimum velocity, don't we? We can use that instead of the source. it's handy. So we've got a random position and a random velocity. Next up, scale. And in this case we're working in a more simple fashion, somewhere between the minimum and maximum scale values by a random amount. What's wrong with that? Oh, I forgot the brackets. The rotation that it spawns with, where it's oriented initially, it's going to be a floating point based on, oh that's when, did I go grey there? I'll check that in a minute. So yeah, we're going to alert between the minimum rotation and the maximum rotation, and we're going to use a random double again. Yes, the float is turned grey. We don't need to cast it to float, it's already a float. Fair enough. The rotation speed, how quickly it rotates from one frame to the other. That's going to be not min rotation, but min rotation speed, and maximum rotation speed, somewhere between those two. Getting a bit long in the tooth, that line, let's split it up. Am I missing anything? Is that done? Texture, tint. If anything else comes up, I'm sure we can come back and add it. So that's going to spawn a bunch of particles and add them to our list. Okay, so far. But then what do we do with them? Well, we need the emitter system to update them. Keep them moving, scaling, whatever they do. Actually, you know what? No, sorry, the update. We'll do two separate updates. That will update the emitter system. I'll come back to that in a sec. But we'll also want to update all the particles within the system, which I think is best kept separate, which we'll see why in a minute. So we'll count the number of particles in the system and have another index for a loop. And this time we're going to go backwards. Instead of going from 0 to count and up by 1, which we could do, that means needing to step backwards every time you remove something, and that can get messy. Instead, we're going to go in reverse. So instead of plus plus, it's minus minus. Instead of starting at 0, we're going to end at 0. Which means we need to begin at the other end. Now we can't just use count because things are 0 based. If there's 10 items in the list, then count will be 10, but there isn't an item number 10, it goes from 0 to 9. So we say count minus 1. Okay, so it's going to look backwards through every element in our particle system. And what should it do along the way? Well, first thing it has to do is check if that particle should still live. So if the particle has a time to live greater than 0, then it continues to do its thing. Let's fill that details in a minute. But if the particle system's time to live is not greater than 0, then it's reached the end of its lifetime, and we take the particle list and remove the object at our position, I. Okay, so how do we keep an individual particle updated? Well, first thing you should do is keep the time to live updated. Oh, okay, if I do minus equals 1, that would work. But here's another thing that's worth learning. That's going to count on a frame by frame basis. So every frame we call update particles, that goes down by 1. So that's basically counting frames. And that's kind of okay, especially at this level. But I'm sure you've heard of frame rate issues that major games can suffer from. And potentially yours could as well if maybe, I don't know, the hard disk delays for some reason. So I'm going to get a game time variable in here. You've probably seen this kicking about inside the other methods. And I'm going to call it game time as well, just to keep things consistent. In fact, you know what, I'll call it GT, just to make it clear this is not the same thing as that, because because that can confuse people sometimes. Same as sprite batch, sprite batch. I think it's a bit confusing. So GT is our game time. We need our main update to pass us that information as a parameter. But when it does, we can then, instead of counting by frame, we can say, hey, give me game time, and tell me how much time has elapsed since the last frame in milliseconds, which is usually going to be 16, but as I say, if there's lag, it could be 17, 20, or whatever it is. And that way it keeps this in sync with the actual time that's passed. So the time to live counts down over time. And eventually it will reach 0, and then that particle will be removed. So that's basically a timer you've got there, handy to use in other situations as well. That kind of technique. Alright, what else? Well, we need to move it around. That's the obvious one. So its velocity. I think first I'm going to apply the slowdown as a percentage to remove. So instead of making it 0.98, which we kind of would have done before, now you put in the 0.02, so 2% slowdown per frame, and we'll just do the calculation here. But also you might have some other kind of acceleration to bear in mind. Typically that's gravity, but it could be wind or it could be something else. We don't know, so we just apply it. And whatever the particle's new velocity is, we can use that to apply to position. I'm playing a little bit fast and loose here. This is not a proper forward Euler implementation. I've really done it the wrong way around, but it should be fine because, as I say, it's just a aesthetic kind of thing. So velocity, then position equal, what are we doing here? Adding on its velocity, aren't we? Okay, so that's it. Accelerating and moving around. There were other things we allowed for, so let's do them too, like the scale. We did that too, didn't we? There was a linear one. There it is. Add on the linear growth. That's what linear means. It's adding on every time period. But also, there was an exponential one, which lets things grow fast over time, or slower, or shrink fast over time. They'll rotate. So the rotation changes by its rotation speed. So whatever its rotation speed is, it gets added on. Oh, but the rotation speed itself changes, doesn't it? Because there is a slowdown involved. What did I call it? Rotation slowdown. Why can't I access that there? What have I done wrong? Oh, it's not in the particle itself, it's in the particle system. So it's just right there. Oh, and lastly, fade them out. Set their alpha, which is held in the tint part. Oh, tint is a colour, what I'm talking about. We want the alpha part of that. I'm going to subtract. This might be tricky. We take the alpha change, and that's a fractional value, so we multiply it by 255. That will need to be a byte, because alpha, as I said before, is a byte. But that could go below 0 and wrap back round to 255. We don't want that. Let's calculate an alpha beforehand. Get the tint for the alpha. Subtract the alpha change times 255, just like we did there down below. And now I'm going to do a conditional operator, something you've not seen before. I'm going to check, let's separate that a little bit. We're going to run a condition first, alpha less than 0. That's the question mark in there. That's basically saying Is it less than 0? And if it is, then we use the byte 0, and this colon separates it from when it's not. So this is kind of an if-else combined into one line. There's our condition, there's the code block for when it's true, and there's the code block for when it's false. I could draw that as a longer if statement, but I'm not going to, because it's nice to learn new things anyway. I think that's right. Alpha less than 0, then 0. But if it's more than 0, then we use that calculation. That makes sense. Okay. Oh, and one last thing. I guess it would be a good idea to draw all our particles. And this is just going to go through each particle in the particles list and do p.draw with the sprite patch. Okay, have I left anything blank in there? Oh, the update, right, okay. Oh yes, I remember now, the update was not going to be updating the particles, but updating the emitter. So we take the time between particles, and we're going to work that out as 1000 divided by the number of particles per second. Sort of like a frame rate would be. It's a private variable, we don't really need to check it every frame, but I guess the user could change the number of particles per second. Then we need to count up to it, so the particles spawn timer, particle spawn timer is going to increment by, we need game time again. Game time, elapsed game time milliseconds, so it's going to count up. I'm going to use while, not if. It's been minus a second. But as long as the particle spawn timer is below 0, we emit one particle, and then make the particle spawn timer go down by the amount of time between particles. The reason for this being, if we have lag or if there's a very small time between particles, you may want to emit more than one per frame. And this is going to loop through, continually reducing the spawn timer until it's no longer reached the point where it should spawn more. Like if the spawn timer is only 10 milliseconds and your frame is 30 milliseconds, so 30 is more than 0, emit a particle, go down by 10, 20 is still more than 0, emit a particle, go down by 10, 10 is still more than 0, emit a particle, and then finish. Basically coping with a rate of emission that's higher than your frame rate, which could happen. Okay, I think that's all for the particle system. I'll pause it there and you can check out how to actually use this system in the next video.